6.1 Regimes as a function of the Reynolds number. The main motivation for the study of viscosity in pipes is due to the great variety of pipe systems in fluid engineering, where why fine spans fluid different shapes. In the basic problems, we find variation by geometry of the pipes. Other components, such as accessories, valves, and bowls and diffusers, design fluid properties. The reason is at a modern Reynolds number, there is a change in the behavior of fluids. The movement stops being smooth and orderly, laminate, and becomes fluctuation and agitated, turbulent. Turbulence can be detected with a hot wire anemometer or with a piezoelectric pressure transducer. Flow apparatus stationary and avalanche but shows rapid on random fluctuation where turbulence is present. This is graphic Reynolds number, where if the flow is laminar, there might be occasional natural disturbance that quickly dampen. B. With a transition begins hatchet of turbulence fluctuation apparatus as the Reynolds number increases due to instability of the laminar movement. C. At R sexuality high the flow fluctuates permanently and is called totally turbulence. Reynolds number fluctuation with typical variables with 1% and 20% of the average spent. They are not strictly periodic, but rather random and distributed in a continuous range or frequency spectrum. In flows with a surface free of turbulence, it can be observed directly. Laminar turbulence. How the turbulence forms inside the tube. It begins to form turbulence bursts of great intensity where a burst has a faster movement from a slower back. Primary parameters that affect the transition is to Reynolds number. This is equation where U average velocity, width, and quantity viscosity. This is graphic laminar turbulence where A and B there is an irregular interface that separates laminar and turbulence flow. D. The burst is cone shaped and less active. Reynolds number behaviors. These are ranges and can vary based on flow geometry, ranges, and levels of fluctuation.
Historical precedents of Reynolds numbers. Turbulent motion is more common than laminar motion. Experimentalists have observed turbulence for centuries, though without perceiving in details. Before 1930, measured instruments were very insensitive and did not pick up rapid fluctuation in scientists only measures mean values, velocity, pressures, and force. In 1839, German engineer Hagen indicated for the first sign the existence of the two viscous flow regimens. In losses to the valid when the flow passes about the certain limited fact when the critical Reynolds number was exceeded. The pressure varies linearly wise the velocity and flow is down 1.1 down 1.1 it's laminar flow and 1.1 and 2.2 and transition is critical and adapt 2.2 it's turbulent flow it is equal at the number Reynolds for practical applications the flow device if the Reynolds number is less than 2000 it is laminar in the degraded time 4000 it's a turbulent between 2000 and 4000 is very difficult to determine which flow it is for the region critical. It is similar and the Hagen. Reynolds in 1883 el British teacher showed that the change is dependent of the parameters velocity, diameters, and kinematic viscosity. Now call it the Reynolds number is the honor. With introduction rod into flow Reynolds observe la transición on turbulencia and rod in the two flows and flow laminar in the matching in 1883. The Reynolds numbers is dimensional flow of the large Reynolds numbers due to high velocity and low viscosity to the turbulence.
And external flows. Both laminar and turbulent flow can be internal, confined by walls, or external and free. In this chapter, we will study internal flows. An internal flows is confined by walls, and the fluid regions subject to the viscous effects will grow and meet until the inner flow is occupied. There is an input regions where the initial on viscous current converges and enters the duct. Viscous boundary layers grow downstream, slowing down axial flow and the wall and accelerating the central core to maintain the continuity requirement. At an infinity distance from the input, the boundary layers are heightened and the non-viscous nucleus disappears. The flow in the tube is the completely viscous and the axial velocity is adjusted. The flow is said to below the velocity profile is constant, the stress on the walls is constant, and the pressures decrease learning in both laminar and turbulent flow. Dimension analysis indicates the Reynolds numbers is the only parameter that determines the input leg. This this image is laminar flow and turbulent flow. This image shows development to speed for profiles and pressures variation and the inlet of a duct. In turbulent flow, for laminar flow, the accepted correlation is this is in turbulent flow, the boundary layers grow faster on the input leg is relatively shorted, following the approximate expression for smooth walls is this.
Have lost friction equation. The coefficient of friction is present as an energy loss in the hydrodynamic equation. The equation is reduced and it is present in the following way as long as it is in a pipe path in which there are no pulls or turbines. This is equation where XL is the friction loss. It is work currently that between point 1 and 2 of the pipe there are moisture transfers, temperature change of pulse and turbines. Friction occurs due to the friction of the fluid on the wall of the pipe through which is moved. This produces a force in the opposite direction to the moving. The friction loss of fluid is referred as the sum of the friction and the height, or also called the variation of the driving line. This is the equation HL. The loss is not only due to the friction between the fluid and the wall, it is also due to the friction between the fluid particles. The same is the way to calculate and currently this loss to the array life problem was discovered by Julius Weisbach, German professor who in 1815 published his test on hydrodynamics in which he chose an equation which gives an answer to this problem. This equation is amply for children follow that fall into a path. This is equation H equal F from L D in D to G, where H is head loss, F equals Darcy friction factor, L equals pipe length, D equals pipe diameter, G equals mean of average velocity on the fluid, G equals standard acceleration of the gravity.
Darcy coefficient. The dimension parameter in equation F is called the Darcy coefficient or friction factor. Henry Darcy was a French engineer who espoused all the high studies on tubes, flows, effects on rockets, etc. To calculate the coefficient, the roots and shape of the pipe must be taken into account since if it is square, triangular or circular, it is calculated differently. He is Henry Darcy, engineer Francis.